software for mathematical computations, sort of building on various other libraries, etc. Okay, and so I will show you some simple calculations that we have done so far. Okay, so just become familiar with the thing. So it's just, I mean, Sage is very, I mean, it's quite large, the sort of things that it can do. But I will just restrict myself to things that you would have seen last semester in linear algebra and things that we have discussed so far. I mean, okay, so that's just to put things on a familiar ground. Okay, so Sage is this. So I'm just going to. Okay, yeah. So I'll just share my screen. Sorry, what is this thing saying? Yeah. Oh, what does it say? Yeah, I hope you're able to see. Okay, so this is Sage. This is a Sage website. Maybe some of you have already seen. Okay. And so as it says here, it's sort of built on Python. Okay, so the language is Python, and it needs. Okay, so it has a typical advanced Python libraries, NumPy, SciPy, SymPy, okay, all those things, and as well as this is a GAP is a group theory calculation thing. So we might use a little bit once we start studying group theory. As I said, this is only bonus. I mean, I'm not going to. There will be no examination, no question in the quiz or the exam will come from Sage. Okay, so but just for. I mean, and also many examples are beyond what can be done by hand, because it's easier to just be able to calculate them. So that's okay. So there are some various things here. Okay, so how to run Sage? Of course, one can install Sage on a laptop and work. Okay, so but for start, I will just show you this online place where you can use Sage. There's a lot of help, online documentation, tutorials, etc., reference. Okay, and again, I don't know. I mean, I probably would have touched like 1% or 2% of Sage altogether in my life, so I would not know much of the things anyway. But there's extensive online help, and there is a website called ask.sagemath.org where you can ask. Okay, so and then there are tutorials of various levels. Okay. Yeah, so some of these, I've read parts of these things, Sage for undergraduates and mathematical computation. I mean, it's not like a math textbook where you start from the beginning and work through till the end. Okay, you just look up whatever. Okay, so the SageMath cell is an online Sage server, so you can just do small computations there. It's a public server, so there are probably a lot of people trying, and it may be slow and things like that. So if you need to use Sage for your research or anything, it's probably better to just install it locally. Okay. So let me just show you how to use that for a start. After that, I will switch to my laptop. This is just so that you become familiar. Okay. So let me. So I have prepared 3 sets of examples, and I'll upload these things to Moodle after this lecture. Okay. So the first part of this session I will just do in the SageMath cell. So I'll just cut and paste. Okay. So I'm defining a matrix. Okay. So this is a syntax. Yeah. So the syntax is. I think it's a superset of Python for most part. But there's some differences that I have read about some operators. Some exponentiation is different in Python and in Sage and something like that. Okay, and so the matrix is defined like this. So matrix is most likely a Python class that Sage defines and not implicitly inside Python. Okay, inside the base Python, it may be the same thing what's there in SymPy or SciPy. That I have not checked. Okay, so this is what you define. Okay, so you can just press evaluate. Sorry, I just said, okay, printed. Yeah, so it printed printed this thing. Okay, so just okay, so this is so yeah, so you have to press evaluate. Otherwise, it's not going to print. Yeah, so, okay, so this is just so it prints matrices like this. Okay, row by row. Each row is a vector. Okay. So that is how. Okay. Now we can define a vector like this. So let us print. So just this is something that confused me also. Matrix. To define a matrix, that it's a capital M, but for a vector it is little v. So again, press evaluate. Okay, so this just prints the vector. So the vectors are. Okay. So just to we can do so one.
Like the first row vector of that matrix.
Let's try. I don't know. Print A0. That printed. Okay. So it's like Python list maybe, right? I mean, the matrix may be built out of Python list. So whatever we can do on list class, we can probably do here also. I'm just guessing. Okay? I have not. Okay? Yeah, as I said, I learn whatever I need at that point, and there's extensive documentation that one just looks up. And actually, if you look at the documentation, most of it has some examples next to it. So one would just learn to write as one goes by. Okay. Yeah, so the indexing is Python level. So it starts from 0. Okay. Let's try. Let us just test. See, index error. So it's a Python error. Index error saying that the list has only 3 elements and Python indices are 0, 1, 2. Okay, and so if you ask for A3, it will create this matrix index out of range. Okay, so this is it's exactly the way Python exceptions and things like that. Okay. So I don't know how much Python you have learned. It's only 2-3 weeks. But I suppose eventually by the semester progresses, you will be able to make more sense of, if you try to keep using Sage along with, you'll be able to make more sense of what these errors mean. Okay, that's my, okay. Yeah, so, okay, so that is, so, okay, so the other thing that, okay, print, oh, sorry, it is throwing up an exception here, so. Sorry, I'm just trying out. Let me see if I can comment it here or itself here. No, probably. Yeah. Okay, so you can just add a comment just by the usual Python comment. So let me just put that in. Okay. Yeah, so W is in the, so one thing that Sage thinks of function application on the left. Okay. So I'll clarify. But one advantage is that if you do this, it actually doesn't complain. Right? It's a 3x1 matrix times 1/3 thing, but it doesn't complain. It just applies. Right? 1, 0, 1, 1 minus 4 just takes the 1. Sorry, how did it get this thing? 1. Sorry, I have no idea how it got -912. Has somebody figured it out? I mean, how did it interpret A times W to get this answer?
So I think it transpose W. So 1 plus 2 times 1 plus 3 times -4 for the first.
1 plus 2 minus 12.
So as in multiplying the first row by the vector. As if you transposed W.
Yeah, correct. So you transposed A and then multiplied by W. Okay. Okay, yeah, I didn't actually, I wrote it, but I forgot to check what it was interpreting. Okay, so now comes the next thing. So see, when you ask for its kernel, it's actually computing its left kernel. This W is the, I mean, we know that this W times A is 0. That's what kernel is saying. Okay. So this is again, it is a choice that somebody made at some point. It was not math textbooks don't do it this way. They will think of this as function argument being on the right side. So it will be matrix times the vector. But I think maybe there are certain, programming advantages if you do multiplication on the left. Okay, so this must be some choice that the developers made because of some. There must be some reason for this. Okay, logically it is all the same, but why this convention differs from what we typically use in math books is. So I didn't read the documentation that carefully, or it's probably explained in those discussion fora, but I didn't bother to check those things. Okay? And one reason is that if you have matrices, if you have two matrices, linear map from V to W to some W prime, linear maps. If you write functions like this, you can just write the matrices like this, and then it will correspond to composition. But if you write in the usual mathematical way, you'll have to reverse the order in which you're writing the matrices. Maybe that is the reason. So I didn't. Okay. So this is one thing you have to keep in mind. When they say kernel, it means left kernel. Okay. Okay. So we can also. So this is just some basics. Okay. We can also solve equations. Okay, so I'm just defining a vector, and I'm asking for it to solve this thing. Okay, A x equals y. Solve that thing. Okay, so this is the answer for the x. Similarly, there is some solve underscore left, etc. Okay? And if you ask, you can just check A times x. Yeah, that's exactly why. Okay. So whatever A times x means, you said it's x times A transpose, right? That thing.
A times x transpose.
Is what?
A times x transpose. So just a normal column vector.
No, that is not what we said, right? Maybe, yeah, correct. A times x transpose, yes. That's exactly what it is solving. Okay. Yeah. Okay, so this is, and the other thing that good to keep in mind is the field on which it is defined. Okay. So the same matrix 2, 0, 0, 1. I'm writing it over 3 different fields: rationals, reals, and complex numbers. Okay. So these are all, rationals is what is, exact computations can be done over rationals. Okay. But it cannot be done over the reals or complex numbers. So there will be some approximation. And if you typically ask for some computation, it will say. Okay. So let us do this. Sorry. Okay, maybe I just do everything. Print AQ, print AR. Sorry, I did this in my own terminal, so I didn't realize one had to write this print or things explicitly. Yeah. So if you ask for AQ, so this is the, maybe just for just, I just want to delimit, just to make sure that there is, yeah. So this is where AQ starts. AQ is this 2001. Okay. When we ask for its real or complex thing, it just puts, it approximates it as some floating point. And I think 53 bits or something. There will be some default, no, sorry, 53 bits is in some other program. Oh, sorry, Sage, I don't remember. But it'll be an approximation. Okay. And so if you ask for its echelon form, okay, this is okay, so we'll get this. So we can ask the same thing, echelon form over. So it's the same computation. Now it's just being written as a real matrix or a complex matrix. Okay, so with all this floating point approximation. Okay, so I hope you got some idea how to do some small computation on the Sage server. Okay, and what else is here? So the things that Sage has interface with, can also do them. Okay, so this is okay. So I just wanted to show you that there is, I mean, if you have to do the small computations, you don't need to install it. You can just do this public server. But I mean, it's probably going to be used by a lot of people. So as you see already, just for this line, there's already like a 1 or 2 second delay before this thing is computed, right? So this is okay. Okay, so now I will switch to my terminal just so that it's a little faster. Okay, so we'll just stop sharing. Okay. Any questions on this so far?
So could you explain solve right again? So I mean, what's the equation?
This what?
So for solve right, I don't understand the equation right.
Oh, okay. I just a minute. Okay, I will just show this in the terminal then. Just a minute. Okay, I will check. It's not like I bothered. Okay, do. Yeah, so just. Okay, let me share my. Okay. Do you see my screen? It is split into, the cursor is moving in some, where I have saved the code, and now the cursors, now I am typing something where the Sage computation is going on. Is it visible? Hello?
Yes, sir.
Yeah, okay. Yeah, so what was the question? So A was defined. The question is, what is the solve right? So yes. I define this vector y, okay? Then I ask it to solve right. So I get something x. Okay? So x I print. So within Sage, so I am just, from my text editor, I am just sending it to Sage. So I don't need to write print. Within Sage, I can just type A. It'll just print A. Okay. So this is an interactive Sage terminal. So I don't know. I mean, this is Linux. I mean, probably same way Mac also. Windows, I do not know. You can just run Sage. I mean, if you run on the command line, Sage will open a terminal in which you can just type Sage commands directly. Okay. So this is it's like the Python interpreter or GHC, which you would have seen last semester. Just a REPL interface. Okay. So yeah, so I just typed. So x is this, and then I ask for a times x, which is a times the transpose of x, right? And that is equal to y. right? So we just solved it. A times x equals, okay, maybe if I write b would be better. Conceptually, would it be better? It just solved ax equals b.
So I think it's fine. Thank you.
This is fine?
Yes.
Okay, yeah. Okay, so now I want to do a slightly different example. Okay, now, sort of echelon form and solving linear equations. So we just saw one example. Okay, so now I want to work with a different matrix. So I define A to be a complex matrix, which is 1. This capital I is the square root of -1, is a square root of -1. So that, then minus I and 1. So this was one of your exercise problems in an earlier week. They find its characteristic polynomial or something like that. I can diagonalize or something like that. Okay, so I ask, so this A dot characteristic polynomial, that is it computes the characteristic polynomial, and its value is x squared. So because we wrote this, it has this approximation of 2, is x squared minus 2x. Okay. That is, that one can just figure out, right? So it will be x minus 1 squared minus 1. So it's x squared minus 2x. Right? Yeah. So its eigenvalues are. So this is just, the file that's below, where the cursor is moving now, it is just like a Python file. Okay? Comments are like Python, etc. Yeah.
So can you also record this and make it available after?
The video, on YouTube.
Yes, like with the usual class.
I didn't want to record it. This cannot. This is not. It's not something that I have prepared well. Okay, so it's. I will make the code available. I think it should be enough.
Okay.
Yeah. After this, I will add a few more comments, etc., and I will make all the code that I used. I will I'll put it in a folder in Moodle. Okay, but I didn't want to record it because it's not a.
Sure, sir.
Yeah.
Thank you, sir.
Yeah. Okay. So now I asked what the characteristic polynomial is. One can ask to factor. So it has factored. Okay, so it must be using some library to do this factoring a single variable polynomial. Okay. And Sage, that's actually sort of the philosophy of Sage. There are existing libraries for various highly optimized libraries for various individual calculations, and Sage wrote sort of a wrapper on top. Not only just writing a wrapper, but various things, and so it sort of seamlessly does this. So the thing, so I have not actually gone through the code, but of these calculations. But most likely, the library that computes the characteristic polynomial will not be the library that does the factorization. They're probably being written by two different. Okay, so maybe if I get time, I will go and look it up some other time. Okay, so this is a factor, and then independently we can ask to ask for its eigenvalues. Okay, so then Python gives some warning, which says using some generic algorithm for an inexact ring. So computations in reals and complexes are inexact as opposed to rationals, okay, or actually finite fields. Okay, so that's so there will be some issues related to numerical precision. But So anyway, but we can, by looking at this, we can now conclude that eigenvalues. This is a comment line. The one that starts with the sharp are comments. Okay, so, so now we have identified eigenvalues. Okay, so now let us do this the proof of Jordan decomposition, sort of manually, and see how it goes. Okay, I mean, one reason why I keep harping on that proof is that it actually teaches some reasonable amount of, it puts in reasonable amount of good linear algebra in that proof. Okay. So in some sense, if you understand what is going on in that proof, you probably have understood some bit of linear algebra. So I ask for the, so now I want to determine the generalized eigenspace for the eigenvalue 0, meaning so we prove this, if you have generalized eigenvalues, their linear combination is also generalized eigenvalue for that same eigenvector, same generalized eigenvector. Okay, so I want to do this for 0. So I'm just going to blindly, I mean, like sort of the least efficient way, try to determine this. I look at the kernel of A. Okay. So again, this is left kernel, but it's okay. I mean, the way we would translate whatever calculation we are doing here to what we did in class would be that we are doing a thing for the transpose matrix. That's all. Okay, but that doesn't affect the eigenspace or rank or nullity and all those things. So just think of this as we are doing the Jordan decomposition for the. So we'll just. Okay, so I'm just going to do this in the most inefficient way I can think of, which is just sit and compute kernel of A square, kernel of A cube, kernel of A to the 4th, and at some point, okay, we conclude. Yeah. So what is it saying? It is saying the kernel of A to the 4th is a vector space of degree 2. That just means it has 2 entries in it. Okay, it is a subspace of C2. Okay, of dimension 1. So it's a one-dimensional subspace of C2 is what this vector space of degree 2 dimension 1 over complex field. Sorry. So this also uses 53 bits of precision. So so if you look at the Sage reference manual or some documentation somewhere, there is a way to do some bit of floating point or double precision numerical calculations with complex numbers. I don't remember the precise way to define it, but there is a way. You can control the amount of precision that you want in these calculations. So anyway, so we just conclude now that the generalized eigenspace of 0 is the span of this vector. I mean, each of this is 1 and minus I. I mean, the vector 1 minus I. Okay. So that is generalized eigenspace for eigenvalue 0 is a span of 1 minus I. Oops, sorry. Sorry, I need to delete. Sorry, I forgot to delete the copy paste. Okay, so now let us determine the generalized eigenspace for eigenvalue 2. So what did we do? We subtract that thing and then compute the kernel of its square and so on. So let us just define B to be this matrix, which is A minus 2 times identity. Yeah, so this is the way one defines identity matrix. Identity matrix, the ring in which you are defining identity matrix. If you do not know what a ring is, don't worry. Just here we are working with complex numbers, so just that field. Okay. And then what size? Okay. So this is what we have. Okay. So this I define as B. Then I ask for the kernel of B. So it says vector space of degree 2 and dimension 1. And actually, since these are distinct eigenvalues, this is all that can happen, but let's just, for the heck of it, let's just compute. Okay, so the conclusion is that generalized eigenvalue for 2 is the span. So I'm just saying that for is this one 1I. Okay. That is the generalized eigenspace for 2. And from these two, from this thing, we can, if you choose this basis, this matrix is diagonalizable, and the diagonal thing is 0 and 2. I mean, Jordan form is 0 and 2 on the diagonal. Okay? That much we can conclude from this. I mean, we could have concluded that from earlier itself, but I was just showing you the calculation for that. Okay. Any questions on this example? Okay, so I will show you. I mean, so one can of course do this stage interactively. So let me quit this. So now I want to. I mean, you can also run Sage non-interactively. Okay, so if you know some computation that we want to run, and you just run a loop. We don't need to do the interactively. So then, so here is the third part that I want to show that way. Okay. So what are we doing? So I have some matrix. This is again from Artin's book. I don't know if I assigned this as an exercise, but one of those things. Okay. So I'm taking a rational matrix. 1 1 0 0 1 0 in the second row and 0 0 1 in the third row. And I just ask it to compute eigenvalues and this set. So eigenvalues is a list. Maybe it's a good idea to just a minute. Sorry, let me just quickly do this little bit of this in interactively just to then I'll show this. So that is a matrix. The part I wanted to show is this. Oops. Okay, I just put that. Eigenvalues. Yeah, so Sage Terminal has this auto completion. So it will you can keep pressing tab and it will show you suggestions and then eigenvalues. Okay, so it's actually 1 1 1 repeated thrice. Okay, so if you're going to do this computation, you should do this only over distinct eigenvalues. So one does this set. Okay, it will just okay. I don't know why I wrote sorted. Yeah, it converts into a list. Okay, so now it has just produced a list of distinct eigenvalues. Okay, so now I'll just quickly go over the code, and then I will just run it without non-interactively. So for t in sort, so t in this list of distinct eigenvalues. Okay, just print eigenvalue. Then construct this B, which is A minus T times identity matrix of that size. Then look at kernel of B, kernel of B square, kernel of B cube. And I went only up to B cube because it's a 3 by 3 matrix. I mean, B will have some, I mean, in this case, B will be nilpotent because there's only one eigen, A has only one distinct eigenvalue. Okay? B will be nilpotent. So B cube will be 0. Okay? But even otherwise, even if there are multiple eigenvalues, the kernel of B this was the computation that we did non-interactively, and all that, yeah. So I was just, I'll just maybe repeat whatever I said towards the end. Yeah. So maybe I will. Okay, so so here what I mean, we guessed what the from the basis how it looked, we noticed that V1 is in the image but not in the kernel. V1 is a non-zero vector in the image, and that goes to the. Okay, so this is the basis. This V1 gives a basis for the image of B, and then we looked at, we sort of built the basis V1 and then V2, which is B times, V1 times B, okay, and then V3, which is independently of this, okay. So what B does is, B takes V1 to V2, and then V3 is 0. So, and these three form a basis, and so that would be a Jordan form. That's what I said. Okay, but I was just trying to show this as an example in which you can do something non-interactively. Yeah. Okay, so that's all I wanted to say. If you, as I said, I don't use Sage a lot, but and I do not know much. Yeah.
For non-interactive purpose, how to save the file? Like, does it has any extensions? If we save the file by that thing?
No, it does. The extension shouldn't matter because it is. At least I don't know about Windows, but in Linux and maybe in Mac, this is determined by what is called file magic. It reads the first 2 bits and decides what sort of file it is. The only place where it might depend on what the extension is, if your editor has some settings which tries to detect what the file's type is by looking at the extension, then it might matter. Okay, let me just try. So I still it. Yeah, well, that is so. The editor has some settings. Has some thing which tries to understand what its configuration, what the file's type is, whether it's Sage file or a Python file or C code or whatever, by looking at the extension. Such things would fail, but you can still run. Even with this, okay, maybe just to search. Sage probably wants extension. Sorry, sorry. Please look up the manual. For non-interactive, maybe Sage does say. Sorry, then I take everything back. Yeah. They are, as far as the operating system is concerned, it recognizes both identically. They are a user bin Sage script, ASCII text. That's all that it is. Okay, but maybe Sage itself wants the file to be named as .sage. I don't know if that is. Okay? Maybe that's the reason why it is complaining. Because it is complaining about this, but it is not complaining about this, right? Yeah, so the Sage program may look at the extension to make some decision along the way. But so if it has an unrecognizable extension, maybe it will complain. But I don't think the operating system cares or knows. Yeah, I don't know. Yeah. Other questions? Yeah, so we will use, once we start group theory, we will do another session on some group theory things. Yeah, okay, so that's my plan, at least so that at least people are interested, become familiar with just the basics of how to use it. Beyond a point, I won't be able to explain, or I would not even know how various things are done. But as I said, the online manual is extensive, and so is the help forum. It's actually very helpful. Okay, so if there are no other questions, I'll stop here. I will upload the files to, I'll add some more comments, and I would upload the files to Moodle.
Sir, as for what we use it for, what do you recommend it for? Like, let's say if like we're working with matrices that are too large for us to multiply, is it for things like that, for instance?
I wouldn't ask, oh, you mean, what should you use? I mean, in class, I don't think, I mean, I would not, I mean, I may not use matrices that are too big to compute, right? But that is all a limitation. And there's only so much I can explain with small matrices. Maybe some, the real, I mean, if you really wanted to understand the proof of Jordan decomposition in a proof, you should probably take some 7x7 matrix or something with some 2-3 distinct eigenvalues, with some 2-3 blocks for each eigenvalue, that sort of thing, right? That will be very difficult to do by hand. You can use this to do that. So yes, I don't know if that's what you asked. Yeah?
Yes, sir. Something along those lines.
I mean, there is a limitation of our ability to do by hand some large matrix calculation, right? We of course make a mistake, right? But so that things, if you want to actually go through that sort of a calculation, so like a 7x7 matrix with some 2-3 distinct eigenvalues, and each eigenvalue with some 2-3 blocks of different sizes. How does the proof go? You can probably visualize it by a few computations in Sage like that, more than what you can do by hand. If that's what, yeah. Okay, other questions? Okay, I'll stop here.